Host from University of North Carolina to tell us about traces, current algebras, and link homologies.
Thanks for the introduction. Thanks also to the organizers for inviting me here. It's been a great program and should be a great week of talks. Indeed, I'm going to talk about, well, definitely traces, definitely link homologies, and, well, if I have time at the end, which I seem to never have time at the end of the talk, well, I'll hopefully say a little bit about current algebras, but otherwise you'll have to ask me during the wine reception tonight, I guess. Okay, so let me start by giving an overview of the general philosophy for the construction we're talking about. So here's what we start with. So given a, well, you could ignore the words in parentheses if you like, a balanced, colored braid, which I'll denote throughout by beta. Okay, if it's not colored, the word balanced doesn't mean anything. If it is colored, for example, I allow colorings by, let's say, non-negative integers. Balance just means that it's closable, so the sort of sequence of labels at the top and at bottom are the same. This is probably not some standard terminology, but it's what I've been writing. I'll talk about this. Okay, so given such a thing, we'll consider the following. So my braid I will picture as some labeling of a box on some strands. So what I'll first do is take a closure. Of course, this is maybe a familiar thing to do if you're trying to define an invariant of knots, to use something like Alexander and Markov theorems to maybe define some invariant of a braid. But let me qualify this by saying I want to take the annular closure, which means that, well, I'll put some puncture point. So maybe this is some step halfway between fully closing the braid and thinking about the link in S3. Okay, and so this thing I'll denote throughout by beta with a hat. And just reminder, this lives inside the annulus cross 0, 1. Okay, all good so far. So the next thing that I'll do is I'll apply some sort of bracket operation. So essentially the Kovanov or Kovanov-Rosansky bracket to get some complex. Okay, again, I'll be talking about the details of all of these steps. Just here's the overview. So again, some sort of standard thing that you would do if you're constructing a link homology theory. Here's where maybe all of the exciting bit happens. I'm going to pass from this complex to a well, simpler, in some sense, one, which I will just denote by the, complex is assigned to the closure, which I'll just denote with this little circle there. So somehow the philosophy of circle is easier in some sense. So both of these will be invariants of braid conjugacy. And then finally, we'll have some fun. What is this fun? Well, we will have functors, which I will label, this is upsilon sub v and t. Those will be some parameters. And we'll take, so apply some functors, take homology, and get at some homology theories, which I'll label fancy h sub v and t. Again, some parameters, which I'll explain later on, to get some vector space valued invariants of the annular closure of this braid. Okay, so that's all in good if you care about invariants of links in the thickened annulus. But, well, maybe a more interesting thing to care about is links in S3. But of course, I could always or standardly embed my annulus cross interval into S3 and consider the sort of usual braid closure, which I will denote by cursive L sub beta. So this is now a link sitting inside S3. And it turns out that for special choices, we'll actually get so special choices of these parameters v and t. We'll get invariance actually of the link sitting inside S3. Okay, so that's sort of the general outline of the construction. Maybe just to say a couple more words before digging into some details. So for special choices of v and t, we'll recover some of our favorite link homology theories. For example, Kovanov homology, Kovanov-Rosansky homology, triply graded link homology. Also annular versions of them follow nicely from this. And well, I should have time to also speculate on some funny new things that seem to come out of this construction, which I'm not sure have been seen before. Okay, but maybe I'll let the audience decide. Okay, so that's the overview. Time to dig in to this story. So I think each of these steps is maybe easier to consider the decategorified level, and I think they're still interesting there. So let's first talk about decategorified. Okay. So first step is easy. Well, I take beta. I just close it. So nothing too new there. But now I want to assign it, well, something like taking the Kovanov or Kovanov-Rosansky bracket. And of course, well, this next step existed, well, way before that stuff. I can do something like the Kaufman bracket. So now apply the following rules. So just formally, I express any crossing as a linear combination of these pictures. So the things on the right-hand side will be some trivalent graphs with edges labeled so that, well, the incoming and outgoing sum of labelings at every vertex is the same. So right now I just need a 2. Okay, and there's some formula for the other crossing, which maybe I'll write like this. Plus that. Okay, and what do I get after applying this linearly everywhere here? So we get, well, I'll just abbreviate this by bracket of beta hat, which is a, say, Z adjoin Q inverse linear combination of, well, we're working in the annulus, so I'll say annular, say GL, doesn't look quite like a G, GL infinity webs. Okay, and what are these things? GL infinity webs? Well, again, they're trivalent graphs, labeled trivalent graphs, which are locally modeled on A, B goes to A plus B, and A plus B splits into things labeled A and B. Okay. So beta to beta hat goes to my bracket. Nothing too exciting so far, essentially just the annular, or maybe the SL infinity or GL infinity version of the annular Kaufman bracket. Okay, So here's where I think the exciting bit happens. So using only upward SLN web relations, which maybe I'll record over on this board. So there's one of these which looks like some kind of associativity, A, B, C, going to A plus B plus C. I won't draw in all of the labels, just enough of them to get the idea. So somehow the point here is that these are some subset of all of the SLN web relations. So there's one of them. Here's another one. A plus B can split into AV, and then rejoin, and I get something like quantum binomial coefficient here. And the third one, maybe the most elaborate. If I start at A and B, give 1 over, give 1 back, subtracting off, doing things in the other order. So first going that way, then going that way. This equals, again, some quantum integer, A minus B, some convention, that thing. OK. So SLN web relations are these plus some more. The important thing is that these ones are, well, upward. I never see any arrows pointing downward. And they're independent of n. So maybe the thing to cite here is a theorem of Countess, Kamnitzer, Morrison, is that, let's say, GL infinity webs plus upward relations plus non-upward relations describes the representation theory of UQ SLN. Okay, so these downward relations are the ones which somehow encode n, and these upward ones are like at n equals infinity.
This is reflecting that you're dealing with a braid rather than a tangle.
Yeah, so I chose at the beginning to work with a braid, and somehow I like braids because they always go up, and they play nicely with these web relations which are independent of n, which also always go up. So it allows me to work at infinity sort of from the start. Okay, great. So let me finish this thought here. Using only upward web relations, we can express this annular bracket as a sum of, again, Z join Q, Q inverse linear sum of concentric labeled circles. So this maps to beta hat sub circle. So that's where that circle is up there. Sort of describes things that are nicely given in terms of circles. So what does this thing equal? Well, this will be some sum over labelings of circles, some Laurent polynomials, and then terms which just look like labelings of circles. OK. Let's see. Do we have time for an example? Sure. It's always good to give examples. OK, maybe for this I'll grab my notes. So let's just start with an easy beta, maybe the easiest interesting beta. So that beta maps to its closure, beta hat, which is just closing this thing, which maps to beta hat bracket, just do unlabeled circles, minus 2 times Q inverse, and something like that, plus Q to the negative 2 times something which looks like that. Okay, and I claim in this case this, so somehow there's maybe a theorem here, maybe it's not worth calling it a theorem, some observation of OL Klefelak and myself. Okay, that you can take this and get everything to just concentric circles. Okay, in this case, it's not very hard. You just apply this relation a couple times. So you slide this bit around, apply that relation, slide this bit around, apply that relation twice. And what do you get? Well, you get obviously this term. When I slide this relation, or slide that around and apply that relation, I'll get things here that just have a 2-colored circle. So Q to the negative 4 minus 1 after some simplification times a 2-labeled circle. Okay. So far, this is maybe just some trick for simplifying some sum. What's the interesting thing? Let's see. I'd like another board. Yeah, maybe this will be fine. Okay, so back to the general theory from our example. So I've taken the bracket that I assigned to the inner closure of this braid. I've simplified it independent of sort of everything. And the point is that specializations of this thing recover quantum link polynomials. Okay, let me be more precise. So I can take this big sum of labeled nested circles, and I can everywhere say that circle labeled A is quantum n choose A, and well, if I have nested circles, I multiply the circles. And what do I get back? Well, up to some normalization, some Rive correction, I get the SLN polynomial of the link in S3 corresponding to the closure of this braid. That's not surprising, right? I've just sort of computed the SLN link polynomial in some elaborate way where I take a stop at infinity before going to the polynomial. You can also get the Hom-Flip polynomial. And okay, maybe let me be a little vague here. You can maybe think about a way to make precise infinity choose A. If you want me to make that precise, I can, but okay, it's the Humphrey polynomial of the wedge A colored unknot. Okay, and you get back the Hom-Flip polynomial. So let me do something which is maybe in some sense surprising and in some sense completely obvious. So I could let my A colored circle, instead of n choose A, go to n plus A minus 1 choose A. And it turns out that, well, as long as I'm careful with my Q's, so maybe I need to switch from Q to Q inverse, up to, again, some normalization given by a Rive correction, I'll again get the SLN polynomial assigned to that link. Okay, and okay, there's some version over here where I maybe let that be infinity plus a minus 1, choose a, but I'll maybe not want to talk about the difference between that and infinity, choose a at the moment. Okay, great, so there's a cool thing that happens is for these two different specializations of my circles, I get things which are the same. Okay, so why is this kind of surprising? I think this is surprising because this evaluation throws away a lot of circles. It throws away circles labeled anything bigger than n. You can't choose n plus 1 things from n. And this one always keeps around all of my circles in my expansion. So on this evaluation, many terms in this sum die which don't over here. Nevertheless, I get the same invariant. It's a little surprising. The non-surprising thing is that, in some sense, this is negative of this, or sorry, it's this taking n to its negative. Okay, and so from that perspective, I'm really not doing much, but just negating maybe powers of q that appear everywhere. Or sorry, taking inverses of powers of q's that appear everywhere. Just somehow also reflected right here. Okay. Let me do an example just to convince you that this isn't all crazy speak. So I could take this and let me focus on these two sort of diagonal evaluations. So I could keep my q like it was, so that somehow this q inverse reflects that I was using q inverse in my positive crossing formula. Evaluate at, say, n equals 2, and I should get the Jones polynomial of the Hopf-Link up to some normalization, and that's what I get. I could also do the n equals 2 version over here, which involves flipping that q to q inverse. And when I do that, I actually end up getting q squared, q to the 4 plus q squared plus 1 plus q to the minus 2. Okay, so now two different ways to get the same like polynomial. So in both cases, this is Jones polynomial.
You're saying like after the Rive correction? Or?
Yeah, after, yeah. I mean, there's some well-controlled rescalings that depend on Rive and maybe some other auxiliary data. Okay.
What is the monomial rescaling?
Sorry?
Is it a monomial rescaling?
Yeah. It's just some global shift at the homological level. Okay. So the idea for the categorified version, so that's still my example, see that there. So idea is, of course, to categorify every step. Okay, which is what we'll do now. I'm going to leave my example floating up there. Come back to it. Okay, so section 3 is the general construction. Okay, how does this start? Well, we can trade the Kaufman bracket maybe I'll put Kaufman in quotes because, well, it doesn't quite look like the original version, but it's some version of that. For the Kovanov-Rosansky bracket, and what does this say to do? Well, this just says to assign some formal chain complex to my crossing. So now my powers of q will denote some degree shifts. And what does the differential here look like? Well, formally, and this can be made very precise, it's this singular cobordism. And similarly, for this other one. Okay. Okay, so I can apply the Rosensky bracket. So what does this do? Well, if I hadn't closed up my braid, this would assign a complex in what I'll call infinity foam to any braid. So what is this? This is a two-category with, and well, I could maybe give an hour or two lecture on just defining this thing and going over some properties, but let me just maybe sum them up. So it's a two-category with one morphisms, these GL infinity webs, and two morphisms are foams, these singular surfaces, modulo some relations, which I won't talk about. It's purely combinatorial construction. So just think about the most natural place for formulas like this to live. And you'll guess something close to the right thing. Okay. Maybe you won't guess the relations, but that's another story. Okay. But we aren't working with our braid. We're working with this annular braid closure. So in this case, this assigns a complex, let's say, of, well, some annular version of this thing. So now our braids are annularly closed. So when I do this resolution, I'll get annular webs and some sort of annular singular surfaces going between them. So there's maybe two ways to think about this, depending on whether you're a topologist or an algebraist. You might prefer one or the other, so let me just write them both down. So this assigns an element of the homotopy category of complexes of, well, this is either just annular foams, so maybe that's something that the topologist would like better. Just, again, webs in the annulus, singular surfaces in the annulus. Okay, you jazz it up enough so you can make sense of doing homological algebra there, and that's what you've got. And this is also can be interpreted as some kind of trace on this category, two category. Okay, and again, in the homotopy category of that thing. Let me do the example.
Wait, the K means
homotopy category of complexes. No, I'll put a 0, and the K will be less fancy if I mean take K theory. Yeah, yeah, too many Ks. Okay. So, let's see. I just want to take the fancier bracket here, and now this will look like some complex where I have that thing with some cobordism there. Direct sum, some cobordism there. So this is the corresponding chain complex. Let me just draw, if I can, one of these maps involved in the differential. So here this would be something like the following. So I have my local singular saddle, and then everything else closed. So it looks like taking a horizontal closure of that picture, where this horizontal trace is trying to describe. Okay. Great. So that's mimicking the first step, just applying the bracket. The next step was this reduction to things that just involve circles. So if the decategorified story was maybe some small theorem, this one is maybe a more involved thing. Let me, state this precisely. So here's a theorem due to Fleck and myself. So what's the quickest way I could possibly say this? Well, the homotopy category of this horizontal trace, so this is taking horizontal closure, that homotopy category is equivalent to some other trace, which I won't define right now, but I'll tell you how to think about it. So remember, this thing should be thought of as just the homotopy category of these annular foams. And what should this thing be thought of? Well, this is the homotopy category of just looking at the restriction to things just involving circles. I should tell you what I mean by that because, well, hopefully it's clear from the web part of this what I mean by circles. Things like that are circles, things like that aren't. But what do I mean for the morphism bit of this? So sitting inside here is a subcategory of these annular foams with objects just, again, labeled concentric circles, well, your direct sums of things and that sort of stuff. Okay, so I'm maybe being a bit imprecise here. There's some grading shifts you can incorporate and some direct sums you'll need to take, but okay, philosophically it's just that. And what are the morphisms? So objects are just circles, which have some S1 symmetry, by definition of a circle, I guess. And morphisms, so I'll put this in quotes and say S1 equivariant annular foams. So for example, here's such a picture, and in fact this is essentially what all of them look like, or all of them are built out of pieces like this. And let me draw in my singular seam. And I'll say with decorations. Okay, so the important observation is that all of these look like web, so GL infinity web cross S1. Okay. Let's see, example first. No, maybe let's state a.
Is just the triangle.
Yeah, just the merge. Yep. And I allowed some decorations. There are some decorations that I could have put on facets here, and I allow them over here too. Okay, so maybe a quick conjecture before I do the example. So before I take homotopy categories of complexes, the thing inside here sits inside of here. And here's a conjecture, is that these things are equivalent before I take homotopy category of complexes. At the moment, we don't know how to prove that. But this conjecture is a theorem for the n equals 2 specialization.
Wait, I'm not understanding what you're saying.
Yeah, so this is a theorem that that is the same as that, as that, as that, but I'm taking homotopy category of complexes everywhere. The conjecture is that I don't need homotopy category of complexes.
You're saying the vertical trace and the horizontal trace are the same?
For these foam categories. That's the conjecture. And it's true for an n equals 2 specialization of this thing and this thing.
Are you actually saying that you do not need trivalent vertices, four-valent vertices in your form?
No, I'm not saying that.
But if any form is a web cross is what?
Mm-hmm.
You must not mean like web cross S1? Is that a picture of a web cross S1?
Just taking a web and I'm rotating it.
But I guess it's hard to imagine how you would ever change your SLM web text. Or
Where is the annulus? The annulus is
yeah, the
running
annulus
around.
is, so this is, yeah, there's an annular core that I was just trying to draw here. It goes straight through everything. So a collection of points looks like points cross S1. And I'm saying this just looks like web cross S1.
No, all your singularities are just closed curves, right?
Yeah, yes.
No four-valent vertices.
No what?
Four-valent vertices.
Four-valent vertices. Oh, sorry, I didn't hear you say four-valent. Yeah, I thought you just said no vertices, and I was like,
Oh,
well,
no,
there's a
no,
vertex
no,
right there.
no,
No, yeah, everything is just built out of pieces like this. So there's somehow you can reduce from webs and foams to points and webs when you're working in the annulus.
Are you saying something about, circles that have got a weight?
Yes,
Is this-
yeah. So there's labels here. They're labeled circles,
Yes.
and all of the facets here are likewise labeled, and they carry again some decorations that you could view it as symmetric functions in the number of variables labeling the facet. Okay. Great. Okay. So yeah, the point I was trying to make with this conjecture is that we know this for homotopy categories of complexes. We don't know it just on the nose for these two categories. So somehow we do something fancy to skirt the issue, and we can work with complexes. It's like a reverse Gaussian elimination homotopy equivalence that needs to get used to prove this theorem in some sense, for people who know.
Do you
what
think
those
you
things
need
mean.
to set infinity to some finite n for that to be true, or do you think it's true for infinity?
I think it's true for infinity.
so there's like an equivalent statement in terms of categorified quantum group, or is that?
Yeah. This is something about the horizontal trace of the Schur quotient of the.
So it's still a Schur quotient. That's what I'm trying to understand.
Yeah. You're on the wrong Howell side. Or sorry, wrong is maybe a a word only should be used maybe not in a public setting, only amongst friends. You are in the other side of Howell duality. Okay, great. Is everyone understanding this board? It's sort of the crucial technical bit of the argument. Okay, so we pass from something which is potentially very complicated webs, complicated foams, down to something which is much simpler, just circles and foams which have some S1 symmetry. Let me do the example. So this complex up here, in fact, this one's isomorphic, but let me just leave it at homotopy equivalent. So somehow the difference here is these things isomorphic or just homotopy equivalent when you pass from these things to the circular versions. Okay, so I take this this complex and I get one which looks like this. So two circles going to say a direct sum of a two-labeled circle and a two-labeled circle in different degree. This map, so I won't draw the actual foams because it's much more complicated than drawing just the web, which it is S1 times. So this map is just 1 and 1 merging to 2. This map is 1 to 1 merging to 2, but I decorate a one-labeled facet. So somehow this is like the calculus of dotted webs. Those are those two maps. And then let me just say everything here is 0. Okay. So using this procedure, we obtain an invariant of braid conjugacy which I'll denote by the complex that I assign to beta, which is built out of circular things. Okay. Okay, so somehow I view this thing as like the like a universal type A invariant of braid closures. The question is, well, what do you do to extract information from this sort of very formal thing? Should apologize for my poor board management. Somehow, if there's more than really just one, I never know where to put them. Okay, so that was the general construction. Let's now talk about link homology. Okay, so I have some invariant of braid conjugacy, which lives in some, well, very abstract homotopy category of some category built out of circles and some singular decorated surfaces, modular relations, which I haven't told you anything about. Let me maybe say just one thing about those relations. If you interpret your foams, your S1 equivariant foams, just as webs, they satisfy these relations. Well, the non-quantum version of those relations. So those relations with Q set equal to 1. So these are relations between relations, let's say, on the maps, on the morphisms here. Well, plus some others involving decorations. So this annularization procedure takes sort of the categories, relations that are held in the horizontal direction and now puts them in the vertical direction. It's kind of a cool thing. Okay, but of course, you interpret each of these things as that thing cross circle, closing it, wrapping it around the core. Okay, now let's talk about link homology. So I have some complex living in some difficult, okay, maybe somewhat difficult place. What do I want? I want a functor from that difficult place to something that's easy to manage, and then I want to take homology. So any functor epsilon from this infinity the foam version, to, let's say, z-graded complex vector spaces, gives a homology theory. For braid closures in annulus cross 0, 1. Just apply the functor and take homology. And let me say for lucky choices, okay, maybe lucky is a bad word, for well-chosen choices, gamma, or sorry, epsilon, we get invariance of links in S3. Okay, so your first question should be how to define such functors. So what do I need? Well, assuming the functor is monoidal, where I guess the monoidal direction here is gluing inside. So I can take a circle, a bunch of circles, and put more circles outside. So assuming I'm monoidal, I have to tell you where one of those circles goes. The circles are just parametrized by integers. Sorry, non-negative integers. So we need vector spaces. It's graded vector spaces V sub A. And we need linear maps. And I claim you actually just need them for the following things. Well, I need to assign a linear map from A, B, merging to A plus B. A plus B merging to A and B. And of course, there's these decorations floating around, but up to relations between the decorations, you really just need to specify one map from the vector space you assign to the number 1 to itself. And if you want everything to be graded, this needs to be degree 2. And that's all you need. Okay, well, which satisfy the relations. Okay. So guessing things to assign to these pictures is, well, something not too tricky. Maybe checking that they're actually well defined is a bit more tricky. But let me state the big result about these things. So this should somehow mimic the fact that from here we just needed to specify where circles went, and we get be some host of invariants. Okay, here we need to specify where circles go and also where these circle equivariant foams go. So somehow the categorified version of this statement. So this is a theorem of Kovalek, Ein, and Antonio Sartori. Okay, stated in this generality. So for each graded super, if you want, vector space squiggly v. The v sub a's over there will be built out of this one squiggly v. This is like just v1. This theorem, we can build everything out of that. So you choose your favorite graded vector space, and you take a degree 2 endomorphism, T, going to the vector space in itself, we get a little space, such a functor epsilon sub vt, which sends, so if I want to know where an A-labeled circle goes, yeah, so maybe let me be a little more precise. So this would be a circle labeled by A. I'll just take wedge A of this V. I'll take well, this dot, it goes where you think it would go. T, mapping from V to V. And I should tell you also where these two things go, but it's actually not so hard to guess once I've told you where the labels go. Well, I want something from wedge A, V, tensor wedge B, V, to wedge A plus B, V. I can just use the projection, and for this one I can just use the canonical inclusion, or, okay, it's actually some multiple of it.
Your endomorphism T is even, right?
Yes.
So what, let's see, what did you say you know about this endomorphism T? What
Degree 2.
Eigenvalues?
That will, well, determine some aspects of the homology theory. So I don't, at the moment, I don't insist on anything. Any T will give you such a functor. Yeah. The question is whether it's actually an interesting one from the perspective of link homology. So let me maybe put in one more word. So we actually could get 2 because, well, there's no reason why I like wedge any more than I like sim. Why don't I really need that 2 in there? Well, sim of a vector space is the same as wedge if I just shift it in superdegree. So shift the, if I allow supervector spaces and shift the even part into odd and odd part into even, then that switches wedge and sim. So you could either think of I have 2 versions, one for wedge, one for sim, or one version and I play around with my superdegree a bit. Okay. Yeah, let's go here. Sorry. Okay, so in the last couple minutes, let me tell you what certain choices recover. So maybe continuing on this theorem for the moment. So specific choices recover known theories. So my first choice is I could let V be, oh, my notes. The Kovanov-Rosansky unknot. I could let T just be multiplication by T, and I could use the wedge version, also known as just putting this thing in even superdegree. And in fact, this homology theory that comes out, which sort of a priori is just an invariant of the braid closure of the annulus, turns out to be the SLN Kovanov-Rosansky homology of the actual link. So there's one specific choice which actually gives you an invariant of links in S3. So here's another choice. I could let V be Cn. Of course, that's the same thing as up there, but I'll view this as the vector representation of non-quantum SLN. I'll let T just be 0. T t being 0 essentially throws away all of the decorations, or all of the bit of this annular foam category which carried decorations, which it turns out was positively graded. So somehow that's like throwing away all of your higher degree stuff and just looking at the degree 0 piece of this annular foam category. And then maybe it's not surprising that should have something to do with the representation theory of SLN, given that all these foams satisfy the same relations. Again, I'll work with the wedge version. And this gives, in this case, this homology theory becomes the annular SLN homology theory, which carries an action of SLN, because all of the maps describe the maps between SL and representations. So let's see, running out of time, so let me give one more case and then maybe quickly draw a picture. So if I let this be the Humphrey homology of the unknot, and let t again be multiplication by t, I recover the triply graded link homology, triply graded Kvanov-Rosansky homology. And let me try to draw quickly a picture. Sorry about depriving you of a minute or two of coffee. So here's how I like to view what's going on here. I have this complex, and for one choice, choosing c to the n, 0, and working with the wedge version, I get this annular link homology. For a different choice, wedge version, I get SLN Kvanov-Rosansky homology. For a different choice, this last choice, I get triply graded Humphrey homology. And okay, if I had a lot more time, I would explain maybe how to describe some spectral sequences between these things in terms of this construction. Maybe that's what you can talk about for coffee. But you'll notice that I didn't tell you anything about what happens over here. Okay, maybe you wouldn't need to ask if I hadn't drawn things in this way. But let me just quickly describe some other things that you could do. And this will correspond to taking this root at the decategorified level as opposed to this one. So I could, again, choose Cn, again let t be 0, and work with the sim version. And I get some annular link homology, so some invariant of the braid closure, but not of the braid closure in S3, braid closure in the thickened annulus. These two are not the same. Just a quick computation convinces you, so I honestly get something new. This again carries an SLN action, which those of you who know about annular Kvanov or annular Kvanov-Rosansky homology know you should expect. And maybe the more interesting thing is if I basically parallel this construction, but trade wedge for sim. So same value, the Kvanov-Rosansky unknot, same t, just multiplication by t, but work with the sim version. Well, I'll get something that I'll call sim hn. And unfortunately, at the moment, I have to write beta hat here. And the point is that essentially by construction, or by that decategorified statement on top of that board, both of these, well, up to some rescalings and regradings, decategorify here. But these are also, as an easy computation shows, are not the same. And maybe let me end on a conjecture. is that this homology built out of the sims is an invariant of the corresponding link sitting inside of S3. Somehow in every example we've been able to check the Markov 2 invariants that you would want to have. We can't prove it at the moment. Okay, I'm probably way over time, 3 minutes over time. Ooh. So I will stop there.
What about if you take the vector representation of GL11?
That's a good question. I don't quite know what to do with my T. I mean, I could sort of build you something very superficial, which just says use a vector representation of GL11 and let T equal 0. Okay, and I could call that annular GL11 homology, but it doesn't have maybe the behavior you would expect. Relating that to not for homology is not something that that I know how to do. And if you really wanted the one for, I mean, annular invariants are nice, but maybe we are mostly interested in invariants of links in the 3-sphere. And I just don't know what to do with T, because, well, T has to be degree 2. It has to do something. I have these 2 vectors, one in even, one in odd degree, super degree. But now I also want to introduce a Q degree, so that I'm degree 2, and nothing, there's no obvious choice. And so we played around with some choices. And
But we hope for something corresponding to Alexander.
Yeah. Well, but if you decategorify that thing, I mean, somehow Alexander doesn't like circles so much, right? Okay. And so this whole thing is built out of circles. So, I mean, maybe there's some way to renormalize. So maybe I should ask you about GL11. But it's, okay. We've been thinking about the stuff on the board has been enough to fill our time so far, but yeah. Yes?
Should there be a reduced version on the sort of the left-hand side of the board?
Yeah, so, I think your student asked us the same question, former student asked us the same question a couple days ago. We chatted a bit. Reducing seems hard in this case because to reduce, I'd like a saddle map. I don't quite have saddles. Somehow every bit which is nasty in like triply graded homology or the bits which seem a little unnatural, we just avoid them by never having an honest thing in S3. It's always just in the annulus. So I'd like to be able to pull in a knot and saddle and reduce by viewing as a module over that. And we don't know how to do that at the moment. So yeah, this is maybe very much at this point a story of unreduced homologies.
For your decategorification of this metric one, do you have to do anything weird with Q, like Q goes to Q inverse?
Yeah. So sorry, it was sort of hidden right here.
So say, okay.
Yeah, to get everything to line up.
Do you think that it's like SL and M, like super, like one is SL?
Yeah, I mean, so one interpretation of this world over here is that this is like GL0N homology, but I don't think it has the behavior that Jake and his collaborators tell us to expect, because I think in that case they actually should be the same, maybe up to some regrading.
What about the OSP theory?
You might make that statement on the reduced homologies.
Okay. Okay, so maybe this is unreduced negative n and yeah.
Okay. All right, well, let's have the rest of the questions over coffee. Or